Hello and welcome back. We are moving on in our journey of renal physiology to the activities of proximal convoluted tubule. So we just got done. Our last lesson was what's taking place at the glomerulus with filtration. We went through the different pressures. We had a net filtration pressure of 10, and any change in blood pressure will affect how much gets filtered. Our volume or our rate of filtration was our GFR, 125 mils per minute. And we have autoregulation and hormonal regulation to keep our kidneys filtering at around 125 mils per minute to keep our blood nice and clean. I just realized as I am wrapping that up that I forgot to mention the autoregulation of GFR. I will mention that here on this next picture. This is our overview of nephron anatomy where we just got done covering what's happening here. So with autoregulation, it was your afferent and efferent, right? Opening and closing and maintaining that GFR. And then hormonal was the juxtaglomerular apparatus, which is releasing renin, angiotensin. The autonomic division, remember rest and digest or fight or flight, only one of those actually innervates the smooth muscle of this blood flow in. It is sympathetic activation of the afferent arterial. So this is in the front door, right? So as blood's coming in, during sympathetic activation, there's a powerful vasoconstriction of the afferent arterial. So if you remember when we were learning about back in chapter 16, fight or flight, one of the effects of sympathetic activation when you're in crisis mode or exercise or fight or flight or freeze or exercise is you reduce your urine production. And that's why is because you get this big vasoconstriction of all your afferent arterioles, which basically shunts the blood back out of your kidneys. So remember, kidneys, lots of blood flow, 4 to 5, all your whole blood volume every 4 to 5 minutes. And so if you're in crisis mode and you need that blood to go to your skeletal muscles to run or to your brain to think, the kidneys are a good place to just kind of shut that down, shunt that blood away from the kidneys back to your brain and your skeletal muscles. Now, it's not going to completely shut down your kidneys because that would be counterintuitive. It just greatly reduces the amount of blood that can go in, slowing down the GFR. And it's temporary. It's supposed to be temporary. Sympathetic activation, fight or flight is a very immediate crisis mode, and then it goes away within a minute or so. It's supposed to be. And then you open that afferent arterial back up and your kidneys are back and running. So it just gives you that short burst of extra blood going other places. So I forgot to mention that last time. I wanted to mention that before we get too far away from that. So what we're going to be doing now is we're going to focus on the events of the PCT. And you can abbreviate PCT, that's fine. PCT, DCT, CD for collecting duct. I'm okay with that. Abbreviations for those things because I will be saying it that way. So hopefully you catch my drift when I say PCT. I'm referring to the proximal convoluted tubule. Now again, proximal because it's close to the beginning, convoluted because it twists and turns all over the place, and tubule because it's a tube. If we take a look at the lining, subcuboidal epithelium lines almost all of this nephron tube. But if you take a look, these cells have microvilli on them. And what do we associate microvilli with? Increased surface area for absorption. So we should expect the structure of the microvilli can determine the function of the PCT, which will be absorption. In this case, it's going to be reabsorption, things that just got filtered out. We want to reclaim those back, the good things we want to reclaim. So, okay, before we move on to the next slides of the physiology of the PCT, I wanted to talk a little bit more, just real quick, a recap of membrane transport, since everything else that we're going to be talking about, all of the physiology of the PCT, the nephron loop, the DCT, and the collecting duct, all have to do with our understanding of membrane transport. So just a quick review. Now this should be review for you from general bio. If you remember, a plasma membrane is made up of a bilayer of phospholipids. I'm not going to draw it all the way across, just here to remind you. Remember the hydrophobic middle, the hydrophilic heads. It has a selectively permeable characteristic, and certain things can move freely through it where others need a little bit of assistance. So let's say we have small lipid soluble items. We have a concentration gradient right? So we have a whole bunch of things on one side of the membrane and very few on the other. So these are small, and we'll say non-polar. You could also say hydrophobic, you could say lipid soluble. They're small in size. And so if that's the case, they can just diffuse right through that plasma membrane passively to try to reach equilibrium. Okay, but that's not everything. We have a whole bunch of stuff that's not small and nonpolar, like glucose or amino acids or vitamins or ions, things that are larger. They can still have a concentration gradient, right? So we still have a higher amount on the top here. So these are going to be big and polar. I like to say large and in charge, right? Large with a charge. So these guys, they cannot diffuse directly through the plasma membrane because that hydrophobic middle repels them. So what they need these membrane channels. So these guys will be able to move down their concentration gradient to try to reach an equilibrium through a membrane channel. Let me actually, this is simple diffusion. This is facilitated diffusion. Okay. So now let's say we'll keep kind of with our green theme here with our large and in charge. It's got its concentration gradient. But let's say we have something else that also has a large gradient here. So purple and blue. And again, these are going to, I'm not going to talk anymore about being the smaller nonpolar. So these are polar, they're big in size. And so sometimes you can get an ion channel or some kind of transport channel. I'll put green in the middle to show that it can do both. You can have what's called co-transport, where two items are moved down their concentration gradient through the same channel. So this is what we call co-transport. Okay, two things moving in the same direction. If we were to have something move in opposite directions, right? So let's get our concentration gradient of green. But maybe we have these red guys here, like this. And again, there's an ion channel that both can go through. So the green's going to go down its concentration gradient. Red's going to go down its concentration gradient. They're going in opposite directions. This is called counter transport. I'm running out of room. I'll write it up here. So in counter transport, substances are going in opposite directions. And if it's passive, those opposite directions have to be going down their concentration gradient. I ran out of room on my membrane here, but the last one that we need to remember is active transport. So if you remember, active transport is using the power of ATP to pump something against its concentration gradient. We might see that in some of these transport mechanisms. So this was just supposed to be a review of how things can travel or be transported across a phospholipid bilayer, since that's what we're going to be dealing with. We have to move stuff from the tubular fluid into the blood, or from the blood into the tubular fluid, and to do that, it has to cross the membranes, the apical surface and the basilar surface of the simple cuboidal epithelium. Okay, so now that we got through that, we can take a look at the PCT. All right, so here is the proximal convoluted tubule, all kind of smushed into one picture of one cell, but no, these processes are going to be happening along the length of the entire cell. I'm going to walk through each one of these individually and kind of maybe keep a tally of what typically is reabsorbed. This stuff moving from the tubular fluid into the blood is reabsorption. Or, so that's our reabsorption right here. Or if we are moving something from the blood into the tubular fluid, we call that secretion. So we're going to take a look at these different things that the job of the PCT is to reabsorb. So the first one we're going to take a look at is glucose. These little purple hexagons, they are representing all organic solids. So it could be glucose, vitamins, amino acids, fatty acids, nucleic acids, things that are like our macromolecules you just worked on in the digestive system, that they're small enough to get filtered out of the blood at that filtrate, but we want to keep them. We can still reclaim them. So we can see here glucose and other organic solids are going to travel with co-transport. Here's a little key, a little green ion channel, bringing in sodium and glucose. So sodium and glucose, following their concentration gradients, passively transported into the cell, and then we see the sodium is facilitated. It's not shown here, but this will be a little channel, facilitated diffusion, and now we have the glucose reabsorbed back into the bloodstream at those paratubular capillaries. Okay, so what we reabsorb, glucose. Now I'm saying using the word glucose, I don't have a ton of room, but remember this is not just glucose, it includes all of those other organic components as well, the organic solutes, vitamins, amino acids, those types of things. And sodium came in with it, and we'll see there's quite other bits of sodium as well. So we have a little leak channel here with a dotted line. So that's again diffusion, things going from a high concentration to low. So we have sodium coming in as a co-transport. We have sodium coming in as this facilitated diffusion. And also take a look, now we're looking at this purple channel. This is a counter transport, right? So they're moving in two different directions. So as sodium is moving in, we have hydrogen that's moving out. Now we should be fairly comfortable with hydrogen ions are going to affect the pH. Our bodies produce a lot of acid, lactic acid, keto acids, amino acids. We have nucleic acids, fatty acids. We've got acids all over the place. So we have a lot of hydrogen ions. So this is a place for our body to get rid of some of those excess hydrogen ions, which we'll be seeing more in chapter 27. So not only are we reabsorbing sodium, but we get to secrete hydrogen ions. Okay. So we see three ways that sodium's coming in. It's coming in with glucose, it's coming in all by itself, and it's coming in as a counter transport with hydrogen ions. Yay, so we're getting rid of some of our excess hydrogen ions to help maintain our blood pH. So then we see, go back to following the sodium, we see the sodium diffusing across the cell. And then here we have that yellow pump. This is a pump, it's active transport, and it should look familiar to you. It is the sodium-potassium pump. It pumps 3 sodiums outside of the cell and 2 potassiums in. We've seen this before. So here, eventually, we are going to be reclaiming sodium. So we've reabsorbed glucose, we've reabsorbed sodium, and we've secreted hydrogen ions. Okay. Now, another thing that we can do if we take a look, oh, hey guys, what's this wonderful equation up here? Looks awfully familiar, right? This is our carbonic acid bicarbonate buffer equation that we saw back in the respiratory system and the digestive system. It's coming back to us. And in this case, it's being driven towards the CO2 product. There's high hydrogen ions in the tubular fluid. We're adding to this right here with our secretion. So if we have high hydrogen or high bicarb, we are being able to drive that to produce water and carbon dioxide. We diffuse the carbon dioxide, it's lipid soluble, so that's going to come in. Here's the equation again, CO2 plus water, carbonic acid, splits. Now we're absorbing more of the CO2, so now this equation is driving in this direction. That hydrogen ion just gets flipped right back out, kind of helps to drive this equilibrium. And take a look at what we've produced. Bicarb. Bicarbonate is a buffer, just like we had the chloride shift. Wake back on the red blood cells when we're picking up CO2 from the peripheral capillaries, we have the same type of thing. We're producing bicarb and we're reabsorbing it, a co-transport. That should be a green. I don't know why that's colored purple. Hey, look, I can fix that. It's co-transport. So the bicarb and the sodium are being co-transported together following their concentration gradient, and now we can add to our list of reabsorption of bicarb, which is great because now we have this buffer in our bloodstream to help us maintain our blood pH. And then the last thing that we're going to reclaim is water. And if you take a look, we have sodium and other solutes like the glucose, amino acids, other things dumping into the peritubular capillary, which is going to make the blood hypertonic to the tubular fluid and to the simple cuboidal cells. So the water will want to follow that solute concentration, and this is helping us reabsorb water. I want to say something, I have my notes here. PCT, like 60% of all of the water, so remember that 180 liters of filtrate, 60% of that water gets reclaimed right away at the PCT. Almost all of the glucose and organic nutrients get reabsorbed. So right after filtering everything here in the glomerulus, the PCT turns right back around and reabsorbs almost all of it right away, putting it back into the bloodstream to get it back into the general circulation. So that peritubular capillary will leave the kidney via the blood supply out to the renal vein back into the inferior vena cava. And we've gotten rid of some hydrogen ions. So the job of the PCT is primarily water reabsorption, salts and organic molecules, a little bit of bicarb, and we can secrete some hydrogen ions. So this is the first part of our proximal, or first part of our nephron, the proximal convoluted tubule. The next video, we're going to take a look at the nephron loop, also known as the loop of Henle, and I will see you in that video. Bye.